I mean, I meant to start it and then I forgot I got into it. So.
Yes,
Right.
we started recording.
Yeah. Okay. So yeah, we were discussing haloarenes, right? So nucleophilic substitution is difficult because of all these factors. So iska reasons. So one reason is resonance. The lone pair of electrons on chlorine is involved in the resonance along with the benzene ring. So that makes it difficult for the bond between carbon and chlorine to break. So substitution ke liye, you need this to leave and something else to take its place. So that if the leaving itself is difficult, yeah, it's going to be difficult. The second reason is hybridization. So haloalkanes mein the hybridization is sp3, haloarenes mein hybridization is sp2. Now between the both of these, which one is more electronegative?
sp2.
Yes. So which one has more S character? Like SPDF mein
sp2.
S has highest electronegativity, right? So more S character is there in sp2, which means that this particular carbon is more electronegative. So more electronegative matlab this bond is going to be stronger, like it's that adds to the difficulty of this bond breaking. So the difference in hybridization also plays a role. Like the bond itself, the bond nature, the characteristic of the bond itself is different. Matlab yeah, that's a factor in the reaction taking place. The third condition is, yeah, so this is something that I had discussed earlier, right? So for nucleophilic, there are two ways for a nucleophile to approach or the reaction to take place. Either the approach of the nucleophile can kick the leaving group, which is SN2 mechanism, or the leaving group can leave and then the nucleophile can be attached to this SN1 mechanism. So in the second case, the phenyl carbocation is highly unstable. So if phenyl carbocation is unstable, this particular carbocation is not favored for its own existence, then obviously like SN1 is completely ruled out. So that's a closed avenue. So that reaction cannot take place. And finally, for SN2 mechanism, even if the nucleophile were to approach this, the benzene ring itself is extremely electron rich. So aromatic, the benzene ring is electron rich, which repels the nucleophile.
So ma'am, the fourth one rules out SN2 mechanism.
Yeah.
So
basically.
hence it does not undergo nucleophilic.
Yeah.
I mean, nucleophilic substitution is not favored when it comes to haloarenes.
Yes. Yeah. So yeah, so when it comes to haloarenes, nucleophilic substitution is pretty straightforward. Very difficult to happen. Only in extreme condition it happens. The one reaction that does tend to happen, like if you had to do it, you have no other option. Benzene is short of supply. You only have like chlorobenzene. You need to prepare alcohol. Then you take that chlorobenzene and treat it with a very strong base, NaOH. So this is like one of the strongest bases in chemistry. NaOH and KOH are extremely strong. At an extremely high temperature, that is 623 atmospheres under 623 Kelvin, under 300 atmospheres pressure. This again, so this is going to result in sodium phenoxide, O minus and Na plus. So there is an elimination of HCl happening here. And this on acidic hydrolysis, so treat it with dilute HCl. Acidic hydrolysis, so this will result in phenol. And so treatment of this, so basically the sodium cation attaches itself to Cl, eliminating NaCl.
Ma'am, sorry. After the first part, why did you write minus HCl?
I'll just move this here for clarity. So what's happening during this process is that there is elimination of HCl.
So ma'am, this is the one and only method which can be used as electrophilic substitution when it comes to haloarenes.
Nucleophilic substitution.
Nucleophilic substitution, sorry.
Yeah.
Okay.
Yeah. So this is like basically the only reaction that takes place. I mean, other reactions would take place, but this itself requires such a high like very specific temperature and pressure conditions. So
can I say that it's not economically favored? Nucleophilic substitution of haloarenes.
yeah, definitely. Like this is not the way you would produce phenol. Like you have lots of other viable methods if at all you wanted to produce phenol. So this is just an example of a haloarene undergoing nucleophilic substitution, just showing how difficult it is. Yep.
Okay, ma'am, got it.
Yeah. So that's why it like you don't even have any generalized reaction or anything like that. This is the only reaction you have with this. Yeah. Noted? Cool. This particular reaction, this is like pure chlorobenzene. Again, special cases, like in case you have any electron withdrawing groups. Examples of electron withdrawing groups, you remember?
NO2.
NO2, yes, awesome.
COOH.
COOH, absolutely. Another one is nitrile group. CN is also electron withdrawing. Yeah. Few examples. Carbonyl, like C double bond O is also electron withdrawing. Yeah. But yeah, in benzene, this particular structure, yeah, these are like the few possibilities you may have. So presence of these, in case these are present at ortho and para positions. So this basically activates the benzene ring. Because the delocalization, like these also get involved in the delocalization. So it activates the benzene ring. And in case they're present in meta position, then there is no effect as such. So this is important because activates benzene ring matlab makes it more reactive. Makes it more like you have clearly defined places where it is electron rich and makes it conducive for reaction, like makes it more reactive in general. Okay. And electron withdrawing groups, ortho and para positions in haloarene. So one is chlorine, and if you have electron withdrawing over here or here, so this activates the benzene ring and this reaction can take place further. I mean, it takes place faster. And if they are present in
Miss,
metaposition,
if it gets activated, that is, it gets more reactive, then doesn't the temperature or something reduce, or the same amount of temperature and pressure is required?
same amount, it just happens faster. See. Cool. So these are like the basic notes about nucleophilic substitution in haloarenes. So in general, it's pretty difficult. So this is like one reaction with NaOH if you had to substitute Cl with OH group. And if like special cases, if you had other like specifically electron withdrawing groups in ortho and para position, activates the benzene ring. So this relates to the different resonance structures that are produced during the presence of, because of the presence of the electron withdrawing delocalization. Yeah, cool. And haloarenes, they undergo electrophilic substitution. Do you guys remember electrophilic substitution?
Yes, ma'am. They undergo 5 types. I don't know about haloarenes, but arenes undergo 5 types of electrophilic substitution.
Haloarenes
I'm
also
guessing-
undergo the same thing.
Oh, all 5 of them?
Yeah, of course.
They
Why
won't
not?
undergo nitration or sulfonation, right? Why would they
Why not?
undergo? I mean, yeah, I can't answer for why not, but I don't know.
They do undergo, but what kind of products do you think will be formed when haloarenes undergo electrophilic substitution?
It'll be like 4 nitro 1 chlorobenzene type of products.
Ortho or para?
Ortho or para, right? Yeah. I mean,
Like
it could
ortho,
be either
para,
of
or
them
meta?
depend. Oh, ortho para.
Ortho para, yes. So
Because
presence of,
chlorine is an ortho para group, right? So it won't
Yes.
undergo meta.
correct. So that's the case with all the haloarenes. It undergoes all the types of electrophilic substitution. The only difference is that the product you're going to get are all ortho-para products.
Okay.
Yeah. So similarly, you guys can do, so this particular thing is chlorination. You guys can solve for the other types of electrophilic substitution also, alkylation, acylation. You guys remember the mechanism of this reaction?
I think so. No.
3 steps.
I don't know. Wait, just a formation of carbocation.
No. Before carbocation, electrophilic substitution ke liye, what do you need?
Electrophile. So formation of an electrophile for producing a carbocation, and then removal of hydrogen or something like that.
That's the 3rd step. Then this electrophile will attack the
attached to the
yes.
aryl ring.
Yes. And so that's when you get the carbocation. So after attack of the electrophile. And then removal of proton. Yeah. So revise this. We have already discussed the electrophilic reaction. The only main thing you guys have to know in this context is that presence of halogen directs the electrophile to ortho-para positions. And it is the same in all this thing, like the whole mechanism behind it is same. The only difference between all of these different types of reactions are the reagents that you use. So you need to use the right reagent so that you get your preferred electrophile. Okay. So Dhriti, Ansh, you guys remember alkylation, acylation ke liye, what do you use? Dhriti, remember? No? Yes, need to revise grade 11 stuff. I told you, organic may everything keeps repeating. Like you just, yeah, just be in touch with the previous things. Yeah, Mitali. So what do you use here?
So for alkylation, for acylation, I'm not so sure. But for alkylation, you use an alkyl chloride.
Yes.
And you use, as a catalyst, you use a Lewis acid, which can be AlCl3.
Correct. AlCl3 or FeCl.
Yeah, that's it. Yeah.
You need Cl minus to go away so that you get R plus as your electrophile. Acylation is the same, just that you have an acyl group, C double bond O Cl, and the same AlCl3. Again, AlCl3 takes away Cl minus, so you will have RCO plus as your electrophile. So this particular part gets attached. And nitration sulfonation ke liye, what do you need?
You use, so for nitration, you use concentrated HNO3 plus H2SO4.
Yes.
I don't know if it's concentrated. Oh, it's called a concentrating mixture. And for sulfonation, you only use H2SO4.
Yeah, extremely concentrated H2SO4.
Provide heat, I think.
That,
yeah.
Correct. Okay, so nitration sulfonation, you need to take away the H, like OH minus. So generally, if you use it in aqueous solution, H plus gets away, you get nitrate ion, but you don't want that to happen. So you use a stronger acid so that the proton from H2SO4 takes away OH minus from HNO3. So then you'll be left with NO2 plus, which will act as an electrophile. So same is the case with H2SO4. You take like really concentrated H2SO4 because it'll act on itself, takes away OH minus, and you get SO3H. Okay. So, I mean, revise this. Last year's recording should be on in the same channel, or else like go through your notes from last year, revise this. In case you guys don't remember, any doubts are there, let me know. Okay. Let's see if I can send any visuals for this reaction also. And that's it for substitution reaction, you guys. Substitution, you have nucleophilic substitution or electrophilic substitution. Nucleophilic substitution preferred by haloalkanes, electrophilic substitution preferred by haloarenes. Okay, and we've got the mechanisms for both. For nucleophilic, you've got SN1, SN2.
Can you just go back to the previous whiteboard ones?
Yeah.
Yep. Thank you. Yeah, got it.
Yeah. Cool. Now comes the second reaction, elimination reactions. Okay. So elimination reaction, again, if you look at the word, there's something getting eliminated. So this involves removal of a small molecule.
Ma'am, isn't saying small molecule very vague?
You won't have whole alkyl groups getting removed. It's usually, you know, something like water, HCl, like what exactly gets removed will depend on what is there, like what is the substituent on this thing. But it's usually like a proton plus, like a hydrogen atom plus whatever is the substituent attached to the molecule.
Yeah.
That's why. So we say small molecule to imply that alkyl groups branches are not getting removed. And
okay,
yeah, like you won't have like a whole benzene ring being removed. It's just 1-2 atom big thing. That's it. So like elimination is a group of reactions. Like if you do elimination on alcohols, water gets removed. If you do elimination on haloalkanes, HCl gets removed. So
Okay.
specifically in the context of haloalkanes, again, haloarenes will not undergo this reaction. This is only for haloalkanes. Because there is a halogen atom being removed and a hydrogen being removed, this is also dehydrohalogenation. D, removal of hydrogen halogenation. That's it. Yeah. Okay. So if you had a haloalkane, here it can be either hydrogens or it can be whatever, R groups. Removal of one hydrogen and one halogen atom minus HX, what will be the product?
Alkene.
Alkene.
An alkene.
Yes. This is getting removed. Carbon needs to fulfill its 4 valency, so they just turn to each other.
So one product of dehydrohalogenation is always like a alkene or like a alkyne
It
maximum.
depends. Yeah. So if you're doing
No, but
it
it's
on,
haloalkanes. Okay, so
Yeah.
alkene only, right?
yes. So this is done in the presence of alcoholic KOH. Yeah. So this is like important to note. If you do it in the presence of alcoholic KOH, you get an alkene. If you use aqueous KOH, aqueous KOH will be rich in OH minus. You're going to do substitution reactions. You'll end up with a
You
substitution.
will end up getting an alcohol.
Yeah.
Oh,
So that's
oh.
one thing you need to be careful about. What reagent is being used here? Yeah. Okay.
So if it's alcoholic KOH, we get alkenes. And if it's aqueous KOH, then we get alcohols.
Yeah.
Okay.
So anything that gives a OH minus, because OH minus is a nucleophile, right? So it's going to force nucleophilic substitution there. So water, then you go towards substitution. NaO, like aqueous NaOH, KOH, it ends up with a substitution that way. Minus HX, right? So the byproduct is HX. Now, this X, the halogen, is always from the alpha carbon. So we call this the alpha carbon because this is where the substituent is attached to. One carbon beside the alpha carbon, you call it the beta carbon. So the hydrogen is always from the beta carbon. Like hydrogen, it won't take hydrogen from a random place. It always takes it from the adjacent carbon atom, whichever is closest. Which makes sense, right? I mean, if you need a double bond to be formed, it needs to be like from the adjacent.
Yeah, it needs to be removed from the adjacent carbon atom.
Yeah. So roughly, if you were to look at the mechanism of the reaction, so you have carbon, carbon, halogen here. Let's say this has hydrogen here. All the other bonds are there. So what alcoholic KOH does is, so this releases an extremely strong base, okay, like which is not OH minus. So like KOH mixed in alcohol, the OH minus attacks the hydrogen from alcohol and like basically gives rise to extremely strong base, like C2H5O minus or something like that, or CH3O minus.
Why does it happen again, ma'am? Oh, just one.
It's the interaction between the alcohol and KOH, simply put. So it's the nature of So you guys had done equilibrium last year, right? Like how acids and bases behave.
Yeah.
Now in water is neutral. Like you have equal amount of H plus and OH minus. So if you put an acid, it's going to
It'll
increase
behave
the
like a
quantity of
base.
OH minus. It's going to release H plus, increase the quantity of H plus. If you put something like ammonia, because they're electron acceptors, it accepts H plus from
It'll
water,
produce what?
relatively
Yeah.
increases OH minus. That way, if you have, let's say, alcohol, C2H5OH. Now, this being an organic compound, you have no set way of figuring out whether this bond is more likely to break or this bond is more likely to break. So that depends on the environment it's in. Like we'll go more over this when we study about alcohols. So when you add a base like KOH, K is always going to be K plus and then OH minus, right? So alcohol is not acidic. Like it's not neutral, it's not acidic. Which means that its conjugate base is going to be pretty strong.
Yeah.
So when this OH minus will attack this particular H, takes away this H, this is going to result in C2H5O minus. So this being the conjugate base of an extremely weak acid, like you won't attribute acidic properties to alcohol, right? Which means that its conjugate base is going to be extremely strong.
C2H5O minus. Okay.
Yeah. So
No,
that
but didn't we? Yeah, you just said we did that, right? If an acid is weak, then its conjugate base is extremely strong. If an acid is
it's a strong acid, conjugate base is going to be weak. So based on that, your really strong base that is developed in the solution. Now, alcoholic KOH is one. You may even take like other really strong bases. This is going to attack H plus. Okay. So because it takes away the H plus, these electrons migrate over here. And because this is getting electron rich, chlorine being more electronegative is going to take these electrons with it. So what ends up happening is you have C double bond C and plus BH plus X minus. Like technically this is what is happening. Like if you get into the mechanism, but overall you can see that one HX is getting eliminated. So this X minus can take the H plus from the solution and then you get your KOH back and this gets eliminated as HX. But this is what is happening from the back end. So the hydrogen on beta carbon gets attacked by the strong base. So B minus is a strong base. So H is taken out. So these electrons migrate to this bond. Carbon is getting electron rich. So the leaving group takes the electrons. Yeah. Chlorine being more electronegative takes electrons. And that's how you get your products. Technically, if you actually look at the molecular level, this is what is happening. But overall, the net thing that you observe what is there in the solution is there is elimination of
HX and formation of an alkene.
Yeah.
That's all we observe. Like,
yeah.
Okay.
Now,
so ma'am, in the examination, when we're asked such questions, there are any question, do we write the elaborate mechanism which is in black or the overall mechanism?
The question will be specific. Like you will be asked if explicitly explain how this reaction happens, or you will be simply asked to write, you'll be given a process like a compound A when treated with this results in a compound B, just write the equation. Then you write only the equation. And then other type of question you'll be asked is, you'll be given the reactants and you'll be asked to write the product. In that case, you just write the product.
Got it.
So the questions will be specific, they won't be vague. All right. So this is pretty straightforward, right? Now, what if you had a compound like this? I had mentioned that any carbon atom which is adjacent to your primary, like the one halogen
It's
is
called the
attached,
alpha carbon atom.
this is alpha, and these two are beta. So when you have two beta carbons, which are, let's say, not equal, like if they're the same, it doesn't make a difference. You just rotate it and you basically get the same product. But if you have two beta carbons that are not equivalent, like this is a CH3 and this only has two hydrogens attached to it. Now, what product are you going to get? So you have two possibilities here. Either you have CH2, like hydrogen is eliminated from this side.
Yeah.
This side is not changed. Or you have elimination happening from this side. So you have, this remains as CH3 and you have a double bond here.
I think it should be the first scenario. Okay, wait. They're gonna get both the products as major and minor thing.
Yes.
Oh.
So which one does it prefer? Like, how do you decide or figure out which one's gonna be major, which is gonna be minor?
So if I was like, I thought we'll get only one product. So I was about to say that we'll get the first one.
Okay, still
yeah.
why? What's the
yeah. So why was because of the inductive effect, maybe because if we look at the CX bond, that CX bond becomes electronegative. So C becomes partially positive. So it will get electrons like from either of the beta carbon atoms. But the one on the right hand side will not be that partially positive, correct? Because it will also get electrons like electrons from the CH3, like the methyl group, but this one will not. So I think it's more likely to lose hydrogen atoms. Like,
so you're saying if this loses a hydrogen atom, it is stabilized because an extra.
It is stabilized due to the inductive. Yeah. So if you ask me which is the more preferable one, I would say the first one.
Okay. First one.
Yeah.
If this is stabilized, then it would rather lose hydrogen from here, right?
Oh, okay. Then I missed out. Then the second one.
Okay.
I mean, yeah, what I thought that if it's not, like, if that is not going to be stable, that means it's unstable, right? The other single methyl group. So it's more likely to lose hydrogen. So I don't know. Okay.
You are correct. That is absolutely right. That makes absolute sense. So
thank God. I was just talking and that was not making sense.
You are making sense. Perfectly fine.
Okay.
So this rule, so basically what happens is, as Mithali said, presence of extra alkyl groups basically stabilizes, like even if this carbon were to lose a hydrogen, it is going to stabilize like whatever is happening here. So yeah, the preference to lose beta hydrogen from the beta carbon is more for the carbon containing or carbon bonded to more number of alkyl groups. So it's like opposite or reverse of Markovnikov rule. So more number of alkyl groups matlab less hydrogen. So more likelihood is for like if the hydrogen will be lost from the carbon atom already having lesser number of hydrogens. You can think of it that way. Okay. So this particular rule is called Sagesef Rule. I think there's like an alternate spelling also that I don't remember. This is what is commonly used, Setsurf Rule. Hi Shantanu, what happened so late? It's like 3:45 now.
I didn't realize what the class.
Oh, so now onwards, yeah, Thursday, Friday, Saturday, just like at least pay attention on WhatsApp. Like you will have classes. And at the beginning of the session, I'd mentioned from now onwards, your classes will be from 2:30 to 5:30. So keep an eye out, okay, from 2:30 onwards. So
I'm sorry, just like a off-topic doubt. So it'll only be on Thursday, Friday, Saturday, right?
yeah, so in case any extra sessions are required, it would be announced. But for now, regular sessions, Thursday, Friday, Saturday.
Yeah,
That's what the schedule
okay.
is made as. Okay.
Yeah, okay. Got it.
Okay. So Shantanu, yeah, so this session is recorded. So you can like revisit it on YouTube again. Go over the notes, like make your own notes, go over it, read the textbook. If there is any part that you're not followed or anything, ask. Okay, next class when we meet. Cool. So right now we finished substitution reactions, electrophilic and nucleophilic. Right now we're discussing elimination reactions. So elimination means a small molecule is removed. Okay, so preferred alkene is the one with more alkyl groups attached to the doubly bonded carbon atom. So 2-butene, this is going to be your major product. And this is going to be minor product. So one way to look at it is the double bond will be formed, like hydrogen will be eliminated where there's fewer number of hydrogens anyway. So this is like a way to, like, it is reverse of Markovnikov, right? You remember what Markovnikov rule says? So Markovnikov rule is applicable for the reverse reaction. When you're adding
Yeah, and it
more
says
reagent.
that your reagent will attach itself to the carbon atom, which is more stable and has less number of hydrogens.
Less number or more number of hydrogens?
Less, ma'am.
No, something that already has a lot of hydrogens, that's where your hydrogen will go and attach.
Oh, okay. Then I'm the anti. Okay.
Yeah. So the substituent will attach to the place with the carbon atom that has lesser number of hydrogens. Hydrogen will go with wherever there's more hydrogens. And Sagesef it's reverse. This is applicable to elimination reaction when you're taking away atoms. Yeah, so hydrogen will be removed where there's already lesser number of hydrogen atoms. That way. Okay. Okay, so another reaction. Oh, what happened to this? Oh, sorry. Another example I have here is, so you have, let's say, H3C, CH2, CH2, CHBr, CH3. Now this in the presence of alcoholic KOH, what product will be formed? I'll give you guys two options. So option A is,
Ma'am, won't both the products be formed as a major minor thing?
yeah, which is a major product formed.
Okay, sorry.
CH double bond, CH, CH3, or B, CH2, this will remain the same. Now this will be CH2, CH double bond CH2. So which would be major, which would be minor? Put your answer in the chat. So Dhriti, Ansh, I'll need answers from you guys also. Shantanu, see, like just based on Setsurf rule, what is mentioned here, see if you can figure out. Mitali's already answered. It's the right answer. Awesome. Got it. Dhriti, Ansh, you guys there? Sending? So which would be major, which would be minor? Awesome. Dhriti also got it correct. Yes. Ansh Gupta is sending.
Miss, like I'm trying to keep my camera on as much as I can, but you know, some part it starts lagging. So whenever it's lagging, I'll shut my camera and then I'll again switch it on. I'm there in
That's
class.
fine. Yeah. Like as long as you're responding, I'm happy. Yeah. That's what I need. Shantanu, are you trying? Like Ansh and Shantanu, are you guys giving the answer? Okay. So Dhriti and Mitali have sent their answer, which is absolutely right. So Setsurf rule says that preference to lose the beta hydrogen more for wherever you have more alkyl groups. So more number of carbon atoms attached basically. So these are the two possibilities to lose beta hydrogen from, because they are one carbon from wherever bromine is. So this or this. Now this particular carbon atom has this whole entourage behind it, more alkyl groups. And this particular carbon atom is just plain CH3, right? So likelihood for losing from this is more because more number of carbon atoms, more alkyl groups. So if it loses a hydrogen, these are going to stabilize it, which means that if this loses the hydrogen, there is double bond formed between both of these carbon atoms, which is what you see in this A wala product. So this is going to be your major product, and this is going to be a minor product. Okay. So A is major and B is minor. Got it? So
ma'am, are there like any other characteristics to Setsurf rule? Like preference to lose a beta hydrogen is more for the carbon atom bonded with more alkyl groups. That I got, but like anything else beside that?
no. So Setsurf rule is just indicative of, it's just a solution to this problem. Like, how do you figure out what logic does this follow? That's all there is.
Okay. Got it.
Cool. That's it for elimination reaction, you guys. I'll just give a quick chart. Like now we have studied substitution.
Sorry. So elimination reaction was only for haloalkanes. We didn't do haloarenes because they don't undergo elimination reaction.
They don't. Like if you look at haloarenes, they've got that double bond delocalization.
Yeah.
All that, right? So
Yeah.
you
Okay.
really can't have an alkyne, like that's a linear molecule. So we saw like substitution to figure out whether it's gonna undergo SN1 or SN2. Again, substitution elimination both had like KOH as a reagent. Now, how do you figure out what reaction is going to take place? Okay. Yeah.
Yeah. So two things. One is alcoholic KOH, which allows us to have elimination reaction, and second one is aqueous KOH, which will give us substitution reaction. So that's an indicator.
That's a very good indicator. Yes, that's one way to look at it. And in general, like I could show you only 1-2 examples. I showed you the general reaction, right? But in exam, what you're going to get is you're going to get very specific ones. You may get a cycloalkane with a Cl attached to, and you have to figure out what reaction is gonna undergo. So few things to keep in mind to figure out which reaction will take place. One is, what is the nature of the raw material you're taking, the substrate, the nature of Rx. Okay. So nature of Rx, if it is a primary haloalkane, then you can straightforward, you can be like SN2 mechanism. If it is secondary, then there is likelihood of either substitution or elimination. So in this case, you need to check what is the nucleophile there, like what is the reagent you're using. And if it is tertiary, again, tertiary also there is likelihood of either substitution or elimination. So in this case, you need to check the stability of the carbocation. So more stable carbocation, then substitution through SN1. Like you can figure that out that way. Then once you've checked the nature of Rx, then you've got your like, okay, what might happen. Then look at the strength or the size of the nucleophile or whatever like base that you're using. Okay. So in the case of alcoholic KOH, OH minus is not your attacking species. The base that is formed, which is much stronger than OH minus, that's the one that's going to attack, which is why it's resulting in elimination. Really strong base. The size also, OH minus, just 2 atoms long, it can just replace the halogen atom. But if you have C2H5O minus, this is pretty bulky. So that's another factor for elimination taking place. Yeah. So what are these different factors? So if it is a bulkier nucleophile, you're going to end up with elimination, which is what is happening in the case of alcoholic KOH. The base that is formed is RO minus, not capable of replacing. And if it is a smaller nucleophile, like in the case of aqueous AOH, for example, OH minus, simple stuff, then it'll go with substitution. Okay. And the third one is general reaction conditions. Reaction conditions, these are again like temperature, pressure. Again, in the case of haloarenes, high temperature, high pressure, you can clearly see that nucleophilic substitution is going to take place. This is like pretty minor, like you don't have very specifics about this. So the main thing focus on is these two. Look at the substrate you're taking, the nature of Rx, and look at the reagent that you're taking. What kind of base, what kind of nucleophile is being produced. Yeah. Smaller nucleophiles end up with substitution, bulkier ones can't like replace, so they end up with elimination. Okay, so this is like just a overall cheat sheet sort of thing. Like it'll help you guide you to the right direction, like if in case you're kind of confused with anything. So it's not like a hard and fast rule. Yeah. The third set of reactions are your reactions with metals.
Miss, I'm sorry, just one thing. You had said that this reaction with metals is like the least important of the lot, right?
Not least important. It's more of, it's not gonna go so deep. Like you have to know about it. There are some parts important. It'll get referenced later on with other preparation methods or like other chemical properties. Like Grignard reagent is one. You guys have come across Grignard reagent earlier in alkanes. We're going to come across Grignard reagent even for alcohols and carboxylic acid and like other things also. So how do you produce a Grignard reagent is through reaction with a metal. So that way there are some reactions, some products that are important, but it's not like substitution elimination where you get into the mechanism of it. It's just reactions. Okay. So starting off with again haloalkanes. Generally, when you have haloalkanes reacting with metals, you get loads of organometallic compounds. All these words are like just pretty logical, like common sense. Organo is organic compound, metallic is it's basically organic compound plus metal, organometallic compounds. Okay, organometallic compounds are in general, like they're a special class of compounds. Mitali, since you're keen on biochemistry, you will be coming across these a lot when you pursue them, because your chlorophyll is organometallic. You have magnesium in within that. Hemoglobin is organometallic, things like that. So those are really complex. You find them in living organisms and such. You have really simple organometallic compounds also. The main thing is Grignard reagent, like the main thing used in laboratories and all, synthesis of other compounds and all, is Grignard reagent. How many of you remember Grignard reagent? At least like what metal is used to produce Grignard reagent?
Is it potassium or magnesium?
Magnesium. So you use Grignard reagent from.
Oh wait, it's R magnesium and X, right?
Yes. So clearly you can see why we are studying it under haloalkanes. So it's literally magnesium getting in between halo and alkane. Okay. So very straightforward. You have a haloalkane, treat it with magnesium in dry ether. Dry ether is like, instead of a water-based equation, is gonna be a dry ether-based equation, organic solvent. You end up with RMGX. Now this is extremely unstable. So whenever you want reactions involving Grignard reagent, you prepare it on the spot. You can't prepare like loads of Grignard reagent and store it somewhere else, because like covalent compounds and metals don't mix. Metals tend to be ionic. They give away electrons and they are cations, right? So even the presence of water, even a little bit of moisture is enough to set this off. Magnesium's gonna go away, form magnesium hydroxide maybe, and this is gonna end up as an alcohol or something like that. So like basically this is extremely unstable, it's highly reactive. So always prepare Grignard reagent on the spot whenever you're doing this. Yeah.
So ma'am, doubt.
hmm?
Whenever we make Grignard reagent, like you said, it needs to be on the spot whenever you're going to use it in the following reaction.
Yeah.
So like, how do you store Grignard's reagent in an
So
order
that's
to
what-
prevent it from?
You don't store it, like you prepare it, and then once it's prepared, you put in your other things, whatever needs to be put
Can
in,
I
put
say that
water
I
or-
just like, I have a test tube, I have Grignard's reagent in it,
yeah,
and I have a beaker, and I have I have a mixture of haloalkane and metal in it. So like what I'm gonna do is just simply pour the test tube in the beaker and not like
with precautions
it
and
in.
stuff, like I mean,
Yeah,
like, you
I
don't want-
definitely that I
But
don't
yeah.
know, but like yeah, okay,
Yeah.
got it.
That's right. Okay, so some points about Grignard reagent: R and Mg, this being carbon, highly covalent, this being a metal. This forms, it is a covalent bond, but extremely highly polar. It's an extremely polar covalent bond, the bond between R and Mg. And Mg and X, again, considering halogens are highly electronegative, they are capable of forming anions, Mg being a metal extremely electropositive.
Covalent by highly polar.
Binary, but that needs to be. And the bond between Mg and X is basically ionic. Because this is highly electronegative, this is highly electropositive. So practically for all like practical purposes, it's basically ionic, even though it's represented like this. Okay.
So it's like two types of different bonding in one simple molecule, and
Yeah.
that's why it's highly unstable.
Yeah. I mean,
Okay.
that's one of the reasons. Like, yeah,
One
like
of the reasons.
this electropositive doesn't mix well with covalent. It
Correct.
can easily break. Yeah. Yeah. So any source of proton, like in the presence of proton, any source of proton, anything that is capable of giving away H, right? Even water for that matter, it is sufficient to set off Grignard reagent, and that basically produces an alkane. That's how alkanes are prepared. Okay.
Could you repeat that?
So any source of proton, like Grignard reagent, if you mix it with any source of proton, so that is sufficient to like break this RMG bond, resulting in alkane. Like the proton attaches itself to the alkyl group, RH basically ends up being an alkane, and this separates out. So any source of proton, like because you want H plus, intuitively you might think, oh, need acids for this because acids give out H plus. Now,
Yeah.
because of the reactivity of Grignard reagent, even sources like
H2O.
H2O and alcohol for that matter.
No, but alcohol also gives out OH, right?
OH may this, like Grignard reagent is so strong that it is, even alcohol being extremely not acidic, it is acidic enough for this to turn into an alkane. It breaks the bond between O and H, so this results in an alkane, and then you have C2H5OMGX that way. So even basic substances, as long as they have a hydrogen, so even amines are enough to, like it is capable of taking hydrogen from amines also, which is like primarily basic. Generally, practical purposes, you treat it as a base. But in this context, for Grignard reagent, it is acidic enough. Oh, you have hydrogen, I'm going to take it. That's what it is. It's going to do. Yeah. So even these are sufficiently acidic. Sufficiently acidic for Grignard reagent. Okay. So all of these compounds on treatment with Grignard reagent are capable of producing alkanes. Okay, clear? Oh, Mithali had gotten disconnected.
Ma'am, I'm sorry. Can you repeat what you just said? I sort of lost like my network
So
and
that you had disconnected.
logged
So I was
Yeah.
saying Grignard reagent is like this bond is so unstable, it is so reactive that any compound, as long as there's like hydrogen atom, it is sufficient for Grignard reagent to take that hydrogen atom and turn into an alkane. So water takes H plus from this. Even acids, alcohols, and even amines. So amines are primarily basic. They're like organic derivatives of ammonia. Ammonia itself is basic. You attach alkyl groups to it, still gonna be basic, like the lone pair of electrons on nitrogen. So even amines, which are generally treated as bases, they have more basic nature. They are sufficiently acidic for Grignard reagent because they've got that hydrogen and
but ma'am, like when I asked a doubt and then I got disconnected. Alcohols give OH, right?
not
Like
again, as I told you, like it depends on the context there.
okay.
So in this context, Grignard, like this particular Mg is electropositive, like it needs negative charge. Like it wants to form an ionic compound. It wants to bond with something rather electronegative. It doesn't want to do covalent bonds. So so like just there being a chance of, like any bond
Swapping.
between hydrogen and electronegative atom, that is sufficient for it. For
Okay.
reagent. Yeah. Okay. So that's like the speciality of Grignard reagent. It's usually it's used as a source of alkyl groups. So alkanes attach it to hydrogen, like alkyl group attached to hydrogen, you get alkane. This is like one of the main ways of preparing alkanes in the laboratory. Prepare Grignard reagent, put some drop of alcohol or water, any hydrogen based thing.
And you simply instantly like get an alkane.
Okay. And in general, other reactions like Grignard reagent is used as, like if you want to attach R to an existing compound with a functional group, like to ethers maybe, or ketones, or like other things. Like basically it's used as a source of pure alkyl group. Like if you want to attach an R group, increase the number of carbon atoms, use Grignard reagent for it. You'll come across context for this. Like we'll come across these reactions later.
Okay.
Okay.
So ma'am, Grignard's reagent is the only way, or there are like other ways as well?
This is like the most preferred way, you can say.
Okay. Why is it more preferred, ma'am?
Because magnesium is a common metal, like you find in the laboratory, you can prepare it readily. And you won't have to worry about other mechanisms getting in the way. Like R and Mg are bound to break. So this R has to get attached somewhere that way.
So ma'am, it's more preferred. Magnesium is a red metal. You can easily make it in laboratory. And
Basically, like it's easily available, and it's a source of alkyl group, because magnesium is, you don't have to worry about this bond breaking, because
okay.
MgCl2 is an ionic compound that's like fairly stable. They both like being with each other that way. Yeah. And then other reaction is like where you have haloalkanes, haloarenes reacting with metals, is Wood's reaction.
And Wood's reaction. Yeah, I studied a lot.
We studied Wood's reaction, right?
Yes. Do you remember what it is?
Yeah.
I
Yeah.
wish.
It is. It doubles the alkane through the course of the reaction.
What are the raw materials you take?
Na
Mm-hmm.
and dry ether.
What are you making Na and dry ether react with to produce your double the number of alkanes?
Haloalkanes. Mainly like like
Yeah,
having a bromine.
bromo.
Yeah.
Yeah, Plus-
bromo haloalkanes or bromoalkanes. I don't know.
bromo
if that's
alkanes.
right.
Halo is
Yeah.
a catch-all word for chlorobromoiodine. Yeah, it's a halogen family, right? So yeah, you studied this for the preparation of alkanes. Now, because you're studying about haloalkanes, it became a property of, how do they react with metals. This you're pretty familiar with. Now, when it comes to haloarenes, you've got Wood's Fittig reaction. This also you're familiar with.
What? We haven't heard it before, ma'am.
So last year, I remember we had
Fittig.
studied Wood's reaction, we had studied Fittig reaction, and then you had Wood's Fittig reaction also, combination of both.
I am not sure.
Okay,
if
so
we did
before
that.
going Wood's Fittig, let's see if you remember Fittig reaction.
Ma'am, for some weird reason, I feel like this is the first time I'm coming across about Fittig.
Oh,
Or it's only me. I'm not sure.
No, even I mean, I've heard the other all. I mean, I don't remember them, but I have heard a fitting reaction. I haven't heard
no? Okay.
fitting.
Fitting is exactly like Wood's reaction, except instead of alkyl, if you have an aryl group. So haloarene, make it react presence of sodium in dry ether. Same thing. It's gonna double this ring. So you end up with biphenyl.
Okay.
This is called diphenyl.
So, ma'am, what is the difference between Fittig reaction and Wood's Fittig reaction? It's the same thing, right?
So Wood's Fittig reaction is a combination of Wood's and Fittig. So you take a haloarene.
And mix it with a haloalkane.
Yes. Mix it with haloalkane plus sodium in dry ether.
Ma'am, but even if you swap the thing, it's still the same thing. No. We get biphenyl, we'll get 2 R's, and we'll get halogen gas.
Huh?
Okay, no, mess that up.
Simple.
Okay.
Like the technique or logic behind all of these reactions is that sodium's gonna kidnap away these chlorines. Sodium kidnaps away the chlorine. Sodium kidnaps away the chlorine or the halogen atom, and whatever remaining organic compound are left, they all like get bonded with each other. So you remove the 2 chlorine atoms from the haloalkane, the 2 R's bond with each other, you end up with double the number of carbon atom wala alkane.
Okay.
What's happening here is you remove the 2X, you'll be left with just 2 phenyl groups wanting, you know, they have an extra bond. So they just like join with each other, end up with diphenyl. So here also sodium's gonna take away the chlorine atoms. So you have phenyl with an extra bond, R with an extra bond. So they both join with each other. So you attach an R to an aryl group. So Wurtz is purely alkyl. Fittig is purely aryl. Wurtz Fittig is alkyl plus aryl.